Section: Introduction. In this section, we outline our approach to problem formulation. We denote an input prompt as X and a response generated by our model, which we represent as hat Y. In situations where there isn't a single correct answer, we create a structured reward function based on specific criteria for each prompt. Each prompt X is linked to a set of criteria, where each criterion has a weight and a binary function that indicates if the response meets that criterion. We normalize the final reward to ensure consistency across different prompts. For explicit rubric aggregation, we evaluate each criterion separately using a generative reward model. While we currently use binary correctness values, our framework can adapt to continuous evaluations. In contrast, implicit rubric aggregation involves passing all criteria and their weights to a generative model, which calculates a single reward score. This model, based on a large language model, takes the prompt, the generated response, and the weighted criteria as input, allowing it to compute a comprehensive reward score. We extend the standard reinforcement learning with verifiable rewards, RLVR, by incorporating multidimensional, prompt-specific evaluation criteria. We clarify that RLVR is a specific case of our rubric-based rewards, where there is only one criterion. This means that rubric-based rewards allow for more complex supervision, accommodating both objective and subjective aspects of response quality. We develop prompt-specific rubrics based on several design principles. These rubrics cover various quality dimensions, such as accuracy and logical structure, and include criteria to penalize common mistakes. We aim for a balance between comprehensive coverage and clarity, typically including 7 to 20 rubric items. Each criterion is assigned an importance level to guide the final reward, supporting interpretable aggregation. We ensure that each rubric item can be evaluated independently, making them actionable without needing additional context. We apply this framework to real-world domains like science and medicine. For each domain, we instruct the model to generate 7 to 20 rubric items based on the complexity of the input question, assigning categorical weights to indicate their importance. These rubrics are designed to be self-contained, allowing non-experts to assess response quality. The evaluation results serve as reward functions in our reinforcement learning process. We generate synthetic rubrics using specific models and release datasets for public use, using reference answers as a guide for creating these rubrics. These sets help train smaller models through either explicit or implicit reward aggregation. Section Summary. In this section, we outline a framework for structured reward functions in reinforcement learning, utilizing prompt-specific rubrics that evaluate model responses based on multiple criteria. We describe both explicit and implicit aggregation methods for these rubrics, emphasizing their ability to provide comprehensive, interpretable, and self-contained evaluations that enhance model training in complex domains like science and medicine. Section: Datasets. In this section, we explore the effectiveness of using rubrics as rewards in two reasoning areas: medicine and science. For our medical dataset, RAR Medical 20K, we compile 20,000 prompts from various medical-related datasets. Similarly, for the science dataset, RAR Science 20K, we gather around 20,000 science prompts aligned with the GPQA Diamond benchmark. Regarding our training process, we utilize the GRPO algorithm with Qwen 2.5-7b as our base model. We train with a batch size of 96 and a learning rate of 5 millionths, following a constant learning rate schedule with a 10% linear warm-up. All models are trained on a single compute node with 8 NVIDIA H100 GPUs. Our training pipeline includes generating responses, where we sample 16 responses for each prompt using a context length of 3,584 and a sampling temperature of 1.0. We then compute rewards using the GPT-4o mini model to evaluate these responses. We compare our results against various baselines and off-the-shelf models, all using Qwen 2.5-7b as the base policy. We also assess the performance of an instruction-tuned variant, Qwen 2.5-7b Instruct. For our rubric-free baselines, we have simple Likert, where the judge model gives a score from 1 to 10 for each response, and reference Likert, where the model compares responses to a high-quality reference answer and assigns a score. For rubric-guided methods, we have several approaches. Predefined RAR uses a fixed set of generic rubrics to compute rewards through a weighted sum. RAR explicit employs prompt-specific rubrics with assigned numerical weights based on their importance. RAR implicit also uses prompt-specific rubrics but asks the judge model for a single holistic rating. In medical reasoning, we evaluate our models using HEALTHBENCH1K as subset of 1000 examples, generating responses with greedy decoding. For science reasoning, we assess models trained on the GPQA diamond subset, repeating evaluations 4 times to ensure accuracy. We permute answer choices and verify responses with a GPT-4o model if necessary, reporting the final accuracy as the average of these runs. Section Summary. In this section, we investigate the effectiveness of rubrics as rewards in medical and scientific reasoning by curating 2 datasets of approximately 20,000 prompts each. We detail our training process using the GRPO algorithm with a specific model architecture, and we compare various baseline methods, including rubric-free and rubric-guided approaches, to evaluate model performance on curated reasoning tasks. Section: Impact of rubric generation strategies in real-world domains. In this section, we explore how different strategies for generating rubrics impact training in real-world scenarios. To do this, we evaluate the Health Bench dataset, which includes a carefully selected set of 3,500 human annotated examples divided into training and testing groups. Our results show that all methods using rubrics perform better than those without, including the reference Likert method. Even the least effective variant of our rubric approach significantly outperforms reference Likert, highlighting the benefits of structured guidance in subjective areas like healthcare. We believe this is due to the detailed and clear rewards that rubrics provide, especially when answers can vary in tone, completeness, or relevance to safety. We also find that the quality of the rubrics is essential. Synthetic rubrics created with reference answers consistently do better than those made without. This emphasizes the need for expert input, whether through human annotations or high-quality reference answers, to create effective rubrics. While synthetic rubrics can be produced at scale, they often fail to capture the nuanced criteria necessary for effective training in critical fields. Next, we assess how the abilities of large language models, LLMs, used for generating rubrics influence performance. We create synthetic rubrics without reference answers and use them to train policies on Health Bench, allowing us to focus on the impact of LLM quality. Our evaluation on a subset of Health Bench shows that larger and more capable LLMs generally produce better rubrics, with GPT-4o performing the best among those without reference guidance. However, all these models still fall short compared to rubrics generated with reference answers. We also note that factors like instruction tuning and reasoning skills are important for effective rubric generation. We then discuss the application of reinforcement learning with verifiable rewards, RLVR, beyond traditional areas like math and coding. The general reasoner model, trained on a diverse dataset, shows significant improvement in performance after fine-tuning. Further studies extend RLVR to fields like medicine and psychology, demonstrating that a single reward model can effectively supervise multiple domains without needing specific adjustments. In healthcare, the MED-RLVR approach improves accuracy in clinical question answering while encouraging reasoning from a large model. Despite these advancements, challenges such as sparse reward signals and limited benchmark coverage remain. We also highlight the use of concise, task-specific rubrics for evaluating advanced LLMs. Research shows that GPT-4 graders using rubrics are more accurate than those relying on a general checklist, although rubrics are only applied during evaluation, not training. The HEALTHBENCH project pairs clinician-written criteria with GPT-4 to assess various aspects like factuality and safety. However, Current methods do not integrate rubrics with verifiable rewards, using them only for grading or generating preference pairs. In terms of learning from feedback, reinforcement learning from human feedback, RLHF, uses numerous human comparisons, but this can introduce noise and encourage reward manipulation. RLVR addresses these issues by using programmatic checks, which can be sparse but are low variance and fully automated. Process supervision offers more detailed feedback by rewarding intermediate reasoning steps. Our rubric-based RLVR approach bridges this gap by transforming rubric criteria into structured verifiers, using their scores as dense rewards in training. Finally, we discuss the interpretability and robustness of our approach. RAR provides a clear alternative to opaque reward models by optimizing against understandable rubric criteria. This transparency may enhance resilience to reward manipulation, as clear criteria are harder for models to exploit than complex learned scores. Future research could investigate RAR's resistance to reward hacking, including scenarios where models try to exploit specific rubric components. Section Summary. In this section, we investigate the impact of different rubric generation strategies on training performance in real-world domains, particularly healthcare, finding that rubric-based methods consistently outperform rubric-free baselines due to their structured supervision. We also highlight the importance of high-quality rubrics generated with reference guidance and the role of LLM capabilities in producing effective rubrics, while discussing the broader application of reinforcement learning with verifiable rewards across various fields. Section: Extending to real-world domains and use cases. In this section, we explore the application of rubric-guided post-training in real-world scenarios and tasks that require agency. We see potential in extending our approach to areas with subjective or multi-step objectives, like using tools, reasoning in uncertain situations, or providing decision support in real life. Here, rubrics can offer organized and specific guidance tailored to each task.